Hi everyone, welcome again. Now we're in chapter 26, Metabolism. We've jumped very close to the back of the book. This one chapter really ties in with the topics we've been discussing, so we typically fit that in around the same time that we're covering cell biology. So even though it's very close to the back of the book, it does tie in very well with what we've been discussing. Today's lecture is actually going to be relatively brief, just kind of a review and introduction to some terms that we're going to be using in the next lecture. Now, the next lecture will be pretty intensive compared to what we've been used to these past several lectures. So, let's start with our not really attendance questions. In a redox reaction, what does it mean if something is reduced? Where does cellular respiration take place? And what is the molecule that the body uses to power endergonic reactions? So go ahead and try to answer these on your own. You may want to go back and refresh some stuff from chapter 2, chapter 3. And some of these terms, hopefully they at least sound familiar to you, even if you don't remember exactly what they are. We've learned them already, and we're going to be applying them in these two lectures. So first, in a redox reaction, oxidation-reduction reaction, what does it mean if something is reduced? Well, when something is reduced, it is gaining an electron. Gaining an electron is reduction. If it were oxidized, it would be losing an electron. So this lecture is really looking deeply at a very specific set of oxidation-reduction reactions. Next, where does cellular respiration take place? It takes place in the mitochondria. So most of this lecture, or the next lecture really, we're going to be looking pretty intently at the mitochondria and exactly what it does and why it earned that nickname, powerhouse of the cell. And finally, what is the molecule that the body uses to power endergonic reactions? Well, first, what are endergonic reactions? Those are reactions that you have to put energy into in order for them to occur. So we kind of usually give the example of a ball rolling up the hill. If we want the ball to roll up the hill, we have to put energy into it. We have to push the ball up the hill or throw the ball up the hill. The ball will not go up the hill on its own. We have to invest energy in it. So that's what an endergonic reaction is. It's a reaction that requires energy input. So what molecule does your body use to power those reactions that require energy? ATP, adenosine triphosphate. And really, when we talk about cellular respiration, it is all about how our body makes ATP. That's what this chapter is going to be looking at. Now, before we start the actual lecture, I want to say chapter 26 is a really big chapter, but we are only concerned with the small section on carbohydrate metabolism. Now, while that doesn't take very many pages, it is a really deep subject. So don't think that it's going to be an easy chapter just because it's very short and we're only looking at part of it. It is going to be a deep chapter. And today's lecture is really just going to be introducing terms and reviewing some things that are going to be important. Chapter 26, Part 2, our next lecture, is going to be looking at the steps of cellular respiration. So, like I said, today is going to be mostly a review and introduction of topics. So let's go ahead and get rolling and talk about metabolism. We introduced metabolism back in Chapter 2, Chemistry. And really what metabolism is, by definition, it's all of the chemical reactions that occur in our body. That's what metabolism means. It is all the chemical reactions that occur in our body. But there are two parts to metabolism. There is anabolism and catabolism. Now, catabolism is what cellular respiration is. There's lots of types of catabolism, but cellular respiration is one example. So this lecture is really going to be looking at a type of catabolism. Catabolism is breaking something that's big down into smaller parts. So we are breaking a lot of chemical bonds when we do that. And when we break chemical bonds, energy is released. So what we're doing is we're getting the energy out of a molecule to power various reactions that our cell needs. Anabolism, on the other hand, is building something larger out of smaller pieces. And that requires energy input. So the catabolic reactions drive the anabolic reactions. We get energy from catabolism and we use that energy for anabolism. And over here on the right, we see kind of a generic cell that shows metabolism in a kind of cartoonized format. So we have large molecules that are broken down by way of catabolism. We get energy out of that. And since we're converting from one thing to another, remember that's inefficient. Some energy is going to be lost as heat. But the other energy is going to be stored as ATP. And then the ATP can be used to take these smaller molecules and build something bigger from them. But again, it's inefficient. So some is lost as heat, some energy is lost as heat. And now we're back. So anabolism and catabolism together are metabolism. Now, in the next lecture, we're going to be using a lot of kind of scary sounding terms that students really tend to freak out about. So what I like to do to prevent that from happening is define the terms today so that when we use them in the next lecture, you already know what they mean. So let's look first at something called phosphorylation. Phosphorylation is really defined as moving a phosphate group from one molecule to another molecule. We're taking a phosphate that is attached to something and moving it to something else. But we could be even more specific and just say attaching a phosphate group to something is phosphorylation. So let's say I have just a generic molecule. We'll call it molecule X. Now, if I put a phosphate group onto that molecule X, I have phosphorylated that molecule X. So phosphorylation, we can just define simply as attaching a phosphate group. Now, there are different types of phosphorylation, and we're going to be using both types in our next lecture. So let's see what those types are. There's something called substrate level phosphorylation, and there's something called oxidative phosphorylation. And the difference is, where did this phosphate group come from? Both of them are phosphorylation. Both of them we are going to attach a phosphate group to another molecule. But the difference is, where was this phosphate group before we attached it to molecule X? In substrate level phosphorylation, this phosphate group was attached to a different molecule. Let's call it molecule Y. In substrate level phosphorylation, we take a phosphate group that is attached to molecule Y, and we move it and attach it to molecule X. So we could say that molecule Y phosphorylated molecule X. Or we could just say molecule X was phosphorylated. Now, that's what we also see over here. Here, this enzyme is aiding in this reaction. We can see this P, this phosphate group, is attached to this green molecule. But during the reaction, we are going to phosphorylate the ADP over here, adenosine diphosphate. We're going to take this phosphate off of the green molecule and attach it to the ADP. Once that happens, what do we have? We have ATP, adenosine triphosphate. That is substrate level phosphorylation. On the other hand, we could have oxidative phosphorylation. In oxidative phosphorylation, the phosphate group is actually not attached to anything. It's just loose in the cytoplasm. And we call that inorganic phosphate. In inorganic phosphate, it is just a phosphate group not attached to anything. And that phosphate group is grabbed by an enzyme and attached to another molecule. So when we talk about this phosphate that isn't attached to anything, this inorganic phosphate, usually it is written as P with a little bitty I next to it. P with a little bitty I next to it. That means inorganic phosphate, and inorganic phosphate just means a phosphate group that is not attached to anything. And in oxidative phosphorylation, inorganic phosphate is attached to a molecule. Moving now to redox reactions or oxidation reduction reactions. This we discussed quite a bit in Chapter 2 also. Now, in oxidation reduction reactions, something is going to lose an electron, something is going to gain an electron. That's what oxidation reduction reactions are all about, following where the electrons go. And remember, we had our oil rig. Let's go ahead and write that up here. Oil rig. And that meant oxidation is losing electrons. Reduction is gaining electrons. So that's how we keep those straight. We also had Leo the lion says grr, or Leo says grr. Losing electrons is oxidation. Gaining electrons is reduction. Whichever of those worked for you, I'm just kind of biased to the oil rig because that's how I learned it. So, cellular respiration, which again is what this chapter is going to be focusing on, is a big giant redox reaction. So, we also said that we're not chemists. This is not a chemistry class, this is a biology class, and we have a hard time seeing electrons in biology class. So, we could kind of substitute the word hydrogen in place of the word electron. So we could say that oxidation is losing hydrogen, reduction is gaining hydrogen. Because we can see those H's. We can see where they go. And it works in biology. Not always in chemistry, but it works in biology. So now let's look at some new terms that we're going to be using in the next lecture. We're going to be talking about two key players called nicotinamide adenine dinucleotide, or NAD+, and flavin adenine dinucleotide, or FAD. Now, you do not need to know what NAD+ and FAD stand for. I tell you that just because they do stand for something, but you don't need to know that big giant set of words that I just used. NAD+ and FAD. We're going to see these guys a lot next lecture. And they are coenzymes, but more specifically, They are electron carriers. When we talk about moving electrons from one molecule to another, or when we talk about gaining or losing electrons, well, these are the guys that actually assist in moving those electrons. Every single time we see NAD plus or FAD, they're going to be doing the same thing. They're going to come up to a molecule and they're going to take hydrogen away from that molecule. Why hydrogen? Because hydrogen contains electrons. So it is their job to take electrons. Now, when they do that, they're also taking protons because, hydrogen is both a proton and an electron. And every time we see NAD plus or FAD, they're going to do the same thing. They're going to take two hydrogens. So they are taking 2 electrons, really. They're going to take 2 hydrogens. And 2 hydrogens means 2 electrons and 2 protons. But it's the electrons that we're concerned with. So, when we see NAD+, it has not yet picked up the electrons. This is like the empty pickup truck or the empty semi that shows up ready to pick up his load of electrons. He is in his oxidized form. Oxidized because he doesn't have any electrons right now. Now, when NAD+ picks up those 2 hydrogens, when he gains those electrons, he is moved to his reduced form. And when he has electrons, when he is carrying electrons, we give him a new name. We call him NADH. NADH. Now, let's kind of talk some details that are not super important for this class, but I want to talk about why sometimes you will see it written NADH plus H plus. When NADH is produced, when NAD plus comes along and takes those 2 hydrogens, he takes 2 electrons and 1 proton and becomes NADH. But that leaves a proton left over. And remember, another way of writing proton is H+. So that's why sometimes you will see it written NADH plus H+. Sometimes you will just see it written as NADH. Because really, NAD plus becomes NADH when he has picked up his load of electrons. FAD is a little more straightforward. FAD is the oxidized form. He is not carrying any electrons. This is the empty pickup truck. He comes along to a molecule and he does the exact same thing that NAD plus does. He's going to take 2 hydrogens. And he takes both 2 electrons and 2 protons. And when he does that, he moves from his oxidized form to his reduced form, and we call him FADH2. So FAD becomes FADH2. FAD is the empty pickup truck. FADH2 is the pickup truck loaded down with his electrons. So that's how we go from the oxidized form to the reduced form for both of these. NAD plus is oxidized, FAD is oxidized. When they pick up their electrons, they become reduced. We get NADH and we get FADH2. That tells us, hey, now we've picked up our electrons. Well, eventually we have to give those electrons away. These are just carriers. They're not interested in holding on to the electrons. They're just pickup trucks. They're transporting those electrons. And at some point tomorrow, or in the next lecture, we will see that we're going to drop our cargo of electrons off. We're going to give them away. So what happens? When we lose electrons, we're going to go back to our oxidized form. So if you see NAD plus or FAD, they do not have their extra electrons that they're carrying. If you see NAD plus or NADH, or if you see FADH2, that means they are currently carrying electrons. Okay, so if that's not super clear, don't worry about it too much just yet. We will see it in action in the next lecture. For right now, just try to listen to those last few minutes of lecture over a couple of times until you kind of get comfortable with hearing those words. One more key player that we're going to see quite a bit in the next lecture is something called coenzyme A, or sometimes it's just abbreviated CoA. Coenzyme A is a molecular chaperone. So what's a chaperone? If someone is chaperoning their son's date, or if they are chaperoning a school dance, what are they doing? They're kind of overseeing something. They're making sure everything is safe. They're making sure everything is okay. Well, coenzyme A kind of does the same thing. When there is a reaction that is about to occur that could potentially fall apart and cause disaster, coenzyme A oversees it and holds on to everyone to show them that everything is okay, and he keeps it from falling apart. There are going to be a few reactions when we look at cellular respiration that if we didn't have someone to hold the molecules together, they would be very unstable and they would fall apart. But coenzyme A holds them together. He keeps everything together and safe. After the reaction occurs, he leaves. Like a good chaperone, after the date is over, the chaperone doesn't need to stick around anymore. And the final bit of review for today is ATP. We talked about this at the very end of chapter 2, but just to review, remember, ATP is a nucleic acid. And like any nucleic acid, it's composed of a nucleotide. So here we see a nucleotide, and specifically, it is a nucleotide of RNA. And remember, in RNA, the 5-carbon sugar that's right in the middle is ribose. So ribose we see right there. And the nitrogenous base is adenine, and we see adenine right there. Now, when we're talking RNA, if we have adenine and ribose together, that's called adenosine. Adenosine is ribose plus adenine. And if we have our phosphate group, we called it AMP, adenosine monophosphate. If we added another phosphate group, we called it ADP, adenosine diphosphate. And if we have 3 phosphate groups, as we do here, we called it ATP, adenosine triphosphate. And that's what this chapter is interested in. We're looking at how we make ATP, because remember, ATP is what powers the reactions in our body. And it did that because there's a lot of energy in that bond right there. How do we get rid of that bond, or how do we break that bond to release energy? ATP will phosphorylate another molecule. And when he phosphorylates that molecule, 2 things happen. Energy is released when this bond is broken. That powers the reaction. Basically, by giving the phosphate group to another molecule, he's giving energy to that other molecule. And second, we go from being ATP to All right, lots of terms there today. Now we're going to start looking at cellular respiration in the next lecture. It will be a little bit longer. It will be a little bit more in detail. So it's a good idea to kind of make sure all of these terms are really clear, because I'm going to be using these terms in the next lecture a lot. If you have any questions before the next lecture, please let me know. And once you get to the next lecture, set aside a good bit of time to maybe watch it at least 2 times, maybe even 3. All right? Take care and let me know if you have any questions.